Hi, my name is Joanna Klicka, and today I'm going to be going through Homework 1 Part B. The problem states, derive the time-dependent material and energy balance equations of the CSTR described, then code, solve, and plot the time-dependent concentration and temperature profiles for the CSTR when the coolant temperature is to 305 Kelvin at time equals 0. So the first thing we want to do is draw out this scenario and derive those equation in variables so that we can understand the situation a little bit better. So we have a CSTR here with some fluid in it. This reactor has a cooling jacket on it, coolant in there. There is a flow into the reactor, the same flow coming out. There's our stirrer. This reactor has a constant volume. There's a concentration going into the reactor, and then there's the concentration inside the reactor, and this concentration is equal to the concentration coming out of the reactor. There's the reaction occurring. We're going to say that it's a first order reaction, and with that we can establish our rate of reaction. R sub A is equal to K concentration, and this is per volume. So to really evaluate this reactor, we want to look at the material and energy balances. So we can start with our material balance. Our material balance is the accumulation equal to the flow of material in minus to the flow of material out minus the amount of material consumed. So starting with the right-hand side of the equation, we have some flow going in, the volumetric flow right now, so that's meters cubed per second, but we want this to be a molar flow rate. So to do that, we can multiply by the concentration, since concentration is moles per meter cubed. So we can cancel these two terms, which will give us moles per second. Now we can do the same thing for the flow going out. Like I said before, it's equal flows going in and out. The only difference here is that we want the concentration going out of the reactor instead of into the reactor. What's being consumed was established by our rate of reaction, but since that is per volume, we want to multiply those terms by volume to get rid of that. So we have volume times K. On the left-hand side of the equation, we want to know how many moles of material are accumulating in the reactor. So right now we know the concentration, which is moles per meter cubed, and if we multiply by the volume, that will give us our moles. I'm going to make this a derivative because we want to know how this changes with time. So V A T. Now we're going to take the volume out of the derivative, since, as I stated previously, the volume is constant. So that gives us V A T. Next, we want to isolate that derivative, so we're going to divide both sides of the equation by volume. A T is equal to C over V times C A minus Ka. And then we have our equation for the material balance. Next, we can move on to the energy balance. This is a very similar situation. We're going to have some accumulation of energy within the reactor, which is equal to the flow of energy into the reactor minus the flow of energy leaving the reactor minus the heat of reaction and minus the heat transfer. There are a couple additional terms, but it still is essentially that accumulation is equal to what goes in and out of the reactor. This time we're going to start on the left-hand side of the equation with the accumulation. So for accumulation, we are looking for some amount of energy. So we want to start with our heat capacity. This is in units of joules per kilogram kelvins. And so to get down to just joules, we're going to multiply by temperature, which would give us joules per kilogram, which means it's still energy per mass. So we could just multiply by mass and get rid of those terms, but since we have so much established already in terms of volume, this doesn't really make sense. Instead, we're going to do rho times V, since density times volume is equal to mass. This scooches over. It's just like before. We are interested in how this changes over time, so we're going to make this a derivative. Now we can switch over to the right-hand side of the equation. So for the energy flowing in, we want to start with our flow in, which is meters cubed per second. We are looking for energy to be in terms of joules per second. So energy is changing with time. And so we need to use that heat capacity again. That is in joules per kilogram Kelvin, multiplied by temperature, just like before. And now this time we have meters cubed per kilogram that we don't want. This is an easy fix since we can multiply by density, since this is mass per volume, and cancel out those terms to get to joules per second. Now we want to make sure that this is our temperature going into the reactor, and then our flow out is exactly the same. We just want to make sure that we're changing that temperature value to the T going out of the reactor. Next we have our heat of reaction, so that term is going to be negative since this is an exothermic reaction, and we also need to add on how fast this is occurring, so we can use that same reaction rate that we did before, remembering to multiply by volume. Okay. And finally we have our heat transfer term. This time this is negative since we do have a cooling jacket, meaning that heat is going to be leaving the system. We are going to start with our heat transfer coefficient, which is per area, so we're going to multiply by the area available for heat transfer. Next, we're going to multiply by T minus Tc, so the temperature of the contents minus the temperature of the coolant. And this is because the driving force behind heat transfer is a temperature difference. Now, finally, we're going to just simplify this equation a little bit. Just like before, we're going to take our terms that are constants and take them out of our derivative and divide both sides of the equation by these terms. So what we end up with is dt is equal to our flow, T in minus T out, plus heat of reaction times K is concentration over rho times Cp minus UA T minus Tc over all those terms, rho Cp. There we go. Now we have our equations for our material energy balances, and we are ready to go ahead and start modeling this reactor in Python using the values given to us in the problem statement. Now we are going to move over to Google Colab to write some of our code. First thing we're going to do is import the libraries that we need. Import numpy as heap from scipy integrate import solve heap from plotly subplots import make underscore subplots. Next, we are going to enter in all of these parameters that were listed in the problem statement. I have those pulled up here on my iPad so we don't have to keep switching back and forth between screens. So first, flow rate at 100 liters per minute. Concentration at 1 mole per liter. Our temperature in at 350 kelvins. Volume at 100 liters. Density at 1,000 grams per liter. Heat capacity at 0.29 joules per Kelvin. Our negative heat of reaction at 5 × 10⁴ joules per mole. And then we have our E divided by R at 8,750 kelvins. Our rate constant 7.2 times 10 meters. With our UA value at 5 times 10 to the 4th joule per minute total. We have our initial coolant temperature at 300 Kelvin. CA naught at 0.5 moles per liter. And our T naught at 350. And then finally we're going to add on that change in coolant temperature to 305 kelvins. Get rid of that. There we go. Now that we have that, we are ready to write our function. we're going to define right-hand side. Independent variable is time, and we're going to have a vector for our dependent variable since we have both concentration and temperature this time. We unpack that. Next, if you notice that we have all these parameters here that we didn't use in any of our previous calculations, and that's because we have to use these to calculate our K value. So we can go over here to do that. So to calculate K, we actually have K is equal to K naught, exponent negative E, R T. And this term here is our activation energy, and K naught is our rate constant. And so we just need to go ahead and actually calculate our K value ourselves. And so we can do that right here. We can do K is equal to K naught times NP times negative ER divided by T. And then now we can just return our right-hand side. So first is our concentration, so that's just the equation that we derived from our material balance. We have Q over V times CA and CA minus K times CA. Next, we have the equation that we derived from our energy balance. So that one is our, so I forgot V here, this should be Q over V. Q over V times T in T plus a negative rate of reaction times K times concentration divided by our density times our heat capacity minus UA times T minus TC divided by density times volume times capacity. Yes. That correct. This whole thing in parentheses here. Perfect. Now that we have that, we need to use our solve IVP function to get some results. But to do that, we need to establish an end time. We're going to go to 10, in this case, I think it's minutes. Yes. Minutes. And then res is equal to solve IVP. Our function is our right-hand side. Our time is 0 to the end. Our initial guesses are CA naught and T naught. Our method is dense underscore output equal to true. Now we are ready to plot this. T plot is equal to NP to T and 200. C A equal to res dot solve T plot. Now we make underscore subplots. We're going to do 1 row, 2, 1 row, 2 columns. Going to add underscore scatter. X is our T plot. Y is CA. Name is CA. And I'm just going to copy and paste. So I need to assign it to a row, so row 1. Column 1. Name. Okay. Copy paste this and change this Y T. Let's call it 2 name T. Layout, make sure that we can see everything clearly. And there we go, we have our plots. Clearly there are some oscillations here, and this is because as we decrease cooling, the temperature in the reactor spikes up. This causes the rate of reaction to increase, which means that more and more of your reactant is being consumed, which we can see here as the concentration goes down. Eventually, the amount of reactant goes down to near 0, as we can see here, which causes the rate of reactant to decrease, which then means that the temperature decreases, keeps decreasing, and as the temperature decreases, the concentration increases and goes back up, and the whole cycle starts all over again, which is why we see these oscillations of going up and down and up and down.